Okay, so today, guys, we are moving into the second half slash third, let's say, of the unit. And that is going to be on probably what is the most important topic in classical physics, okay? And that is the work energy theorem. Without the work energy theorem, none of the other stuff we've gone over happens. Okay? Energy has to come from somewhere. Okay? If you want to get something moving, the energy that it receives has to come from somewhere, and that's because work is done on it. On the very first day of this unit, we talked briefly about that. Okay? How a change in thermal energy is called heat, whereas a change in mechanical energy is called work. Okay, so what we're looking at today is all to do with mechanical energy, okay, and how we change the mechanical energy of an object and what that looks like. Okay, so the big thing here, guys, is this. The takeaway that we're going to go over time and time again in this lesson for the rest of this unit is this. Work, okay, work is a change in, so delta means change, mechanical energy. Okay, En. In Science 10, what that's going to mean for you is this. Either the kinetic energy of the object will change. Kinetic energy is the energy you have because you're moving. Okay? Or the gravitational potential energy will change. That means you'll go higher or lower. Okay, so it's going to be one or the other of those two situations. When you get to physics 20, they can both change together. All right, we don't do any of those in science 10. So your big challenge will be to read a problem and determine what kind of energy is being changed by the work that's being done. Okay, so if I do this, okay, and I pick up my coffee cup and I lift it up off the desk, have I done work? Okay, how do you know? What does my coffee cup have now, or more of, than it had on the desk? Potential energy. Yeah, it has more gravitational potential energy because it's higher off the ground. Okay, and the reason it got higher is because I picked it up and lifted it. Okay, I did work. I transferred mechanical energy, in this case gravitational potential energy, to it when I lifted it. All right. If I have this cart, okay, right here, and I give it a push, okay, it sped up initially. Then it slowed down after I was done pushing it. Okay, did I do work? Okay, how do we know? What was the evidence of that work? What did the cart do? It moved. Okay, it went from a velocity of 0 to some other velocity. We don't know what because we didn't really measure it. Okay, but does that mean that I gave it kinetic energy? It does, because it didn't have it before I pushed it. Okay, I did work. All right. Now, in both of those situations, okay, the work was the same, and I don't mean like the same number. I mean done in the same way. If you're going to do work, that is, you're going to give energy of some kind to something. Okay, you have to do this. You have to exert force. Ooh, that's terrible. Try that again. Make a different color. It's a terrible background color. You have to exert force. Okay, so you have to push or pull the object through a distance. In other words, you have to make it move. Okay? You're not doing any work if you don't make it move. Okay? So work is done when the mechanical energy, either kinetic or potential or both, of an object changes. And the way you make that change is by exerting a force through a distance. Okay, when I pushed the cart, I exerted a force. Okay, my arms straightened. That would have been the distance over which I exerted the force, the length of my arms straightening. Okay, when I lifted the coffee cup, it would have been the distance from the desk to the position of the coffee cup after I lifted it. Okay, there was a distance, there was a force. There was me lifting or me pushing, okay, in either case. That has to be present for work to be done. Okay, everybody all right with that idea? Okay, so energy, okay, just like motion, is not so much a measurable quantity, but we can calculate what goes into it. Okay, so we can give it a value. Okay, we can quantify it. We can say it's this many joules. Joules are the units for energy. Okay, so energy is a measure of an object or a system's capacity or ability to do work. Okay, so if something has energy, it can do work. Right now, in its present position and condition, can this cart do any work? Right? It's not moving. It's already on the ground. Can't fall any further. Okay? It has no capacity to do work. Therefore, this cart has no energy. It has no gravitational potential energy. It has no kinetic energy. Okay? It isn't doing anything, and it doesn't have the ability to change that. Okay? When it was rolling, could it do work? Yeah. If someone had stepped in front of it, it would have hit them. Okay? It would have done work on them, changed their shape. Okay? Something like that, maybe made them move a little bit, right? So you have to have energy to do work, all right? So here's what that means. It means that, if we get like in the wintertime, we get a whole bunch of snow, mom or dad wakes you up and go, hey, go shovel the driveway, and you're like, I have no energy, I can't do that. You're lying. You absolutely do, because you're not dead, okay? You have energy, okay? You just don't want to, right? But if you have energy, you can go out and do the work required to clear the snow. That means you're going to exert a force through a distance, you're going to lift the snow, you're going to pile it up on the edges of the driveway, okay? And that'll be the evidence of your work. Okay? The mousetrap there, does it have energy? In the condition it's in right now? It absolutely does. Okay? If something stepped on the trigger, it would snap, okay, because it's loaded right now. Okay, how do you load? Anyone ever loaded a mousetrap before? Okay, so if you load a classic mousetrap like this, okay, there's a big spring here, right? So right here, big spring. So in its triggered position, the killing bar, that's what it's called, it's aptly named, that's its job, okay, would be over here. All right, in that condition, it doesn't have any energy because it's already been triggered. But in order to put it like this, to set the trap, you have to pull the whole killing bar apparatus, which bends the spring. Okay, are you exerting a force through a distance when you pull that bar to the other side? Okay, so what kind of energy would this thing have in this condition? Kinetic or potential? It has potential energy. Not gravitational. In this case, it has elastic potential energy. You've done work to change the shape of the spring, and when you do that, you put elastic potential energy in it because the spring wants to go back to its original shape. Same as when you pull back on a rubber band or slingshot or something like that. Okay, you pull back, you exert a force through a distance. Now there's elastic potential energy in that spring because if you let it go, it'll snap back to its original shape. Okay, everybody all right with that? Now, if something triggers, so steps on the trigger, okay, this mousetrap, then it will snap back. What will all that elastic potential energy be turned into? Somebody whispered it. Okay, I heard kinetic somewhere. Okay, so it'll turn into kinetic energy because the killing bar will get moving, right? That spring will unload it, okay, and it'll make it move really, really quickly. Kinetic energy is what really does work, okay? Because it has to be moving to do something, right? Like that coffee cup sitting on my desk right now has gravitational potential energy. It only has potential energy. It has the potential to do work. I have to knock it off the desk before it's actually going to do anything. Okay, everyone kind of follow the difference? So energy is the capacity to do work, but in some cases with potential, you have to release the potential. You have to convert it into something else in order to make it work. Okay? All right. That okay with everybody? Okay, so I exert a force through a distance to set that trap. okay? And then the spring does the same thing. If that trap is triggered, it exerts a force through the bar that accelerates it to a high speed, okay? Giving it kinetic energy and the ability to do work on some poor mouse, okay, when it hits it. Right? Pretty simple energy conversions there. All right, so definitions here, okay? Definitely know these definitions, okay? Energy is a measure of an object or a system's capacity to do work, and work is the transfer of energy from one object or system to another. So, how do you get energy? How do you get mechanical energy? Right now the cart doesn't have any mechanical energy. How can it get some? By doing work. If somebody goes and does work on the cart, it will gain energy because work is a transfer or a change in energy. Okay, transfer from one object to another. Okay? But in order to do work, you have to have energy. Does that seem like a chicken and the egg kind of a question? Like you have to have one to have the other, but you can't get one without the other? Okay, by the way, the answer to which came first, the chicken or the egg, is obviously very clear. The egg came first, because birds evolved from reptiles and reptiles lay eggs. Eggs came first. I don't know why people think that's a hard question to ask. Okay, or answer, but it's an easy question to answer. Eggs came first. Okay? Now, in this case, it isn't so clear. Okay? I can't have energy unless work is done to me. Okay? But whatever does work on me has to have had work done on it in order for it to have energy. Okay? So it's very much a kind of a chain of events that has to occur. Now, can I convert other forms of energy into mechanical energy? Yeah. That's how we move around. We convert the chemical energy in our food into mechanical energy through our muscles. Okay, so as long as you have some kind of energy, you can convert it to mechanical and do work. Okay. All right. Now, work energy theorem is kind of one of the big things that we use in sports science. Okay, so the development of better equipment, better technique, okay, all of that kind of stuff. Work energy theorem is a key part of that. Okay? So if we take something like fairly simple, like a tennis serve, okay, what do you suppose determines how fast you can serve the ball? Basically two things. The same two things that determine how fast you can hit a slap shot. Okay, or how fast you can hit a golf ball. Force and distance. Remember, in all three of those situations, you're trying to give the object kinetic energy. The tennis ball, the golf ball, okay, the hockey puck. You're trying to give an object mechanical energy in the form of kinetic energy. The only way you can do that is by doing work on it. And the amount of work that you can do is affected by two things. How much force you can exert and the distance over which you exert it. Okay? So this one has to do with your strength. This one generally has to do with either your equipment or your technique or some combination of both. Right? So, two sports work like this. Tennis and pickleball. How many people have played both? Okay? There's a reason that pickleball is the sport of old people. Okay? Because they don't use a racket, they use a paddle. Can you swing a paddle as fast as you can swing a racket? Why not? Can the air go through the racket? Air can go through the racket. Can't go through the paddle. It goes around the paddle. Also, pickleball paddle, it's only about this long. Tennis racket, much longer. Okay? Can you get the tennis racket moving a lot faster than the paddle? Therefore, tennis is a faster game. Okay? Now, how fast you serve a tennis ball is based on your strength. Okay? So how fast can you swing the racket? And how long can you be in contact? And by long, I mean distance. Over what distance can you be in contact with the ball? This is another reason why tennis is faster than pickleball. Okay? When the tennis ball hits the pickleball paddle, it hits it and bounces off right away because the paddle is solid. Okay? But because a tennis racket is made of strings, when the tennis ball, so if this is the frame of the racket, the strings can actually act almost like a net. They get pushed back when the ball hits them, right? They get stretched. So if the ball is against the strings and the strings can stretch, can I be in contact with the ball over a greater distance than if I hit it with something solid that bounces right off? Absolutely. So if I have the same person swing a pickleball racket versus a tennis racket, they're always going to serve the ball faster with a tennis racket because this part of the equation will be much bigger. They will be in contact with the ball over a larger distance, and thus they will be able to do more work. They'll exert the same amount of force because it's the same person. They have the same amount of strength. Okay? But because the tennis racket works differently, they'll hit the ball faster with the tennis racket. Okay? That making some sense? Okay. Another sport, we talked about this, hockey. Okay? Hockey, the material sticks are made out of now is very different than when I was a kid and played hockey. Okay? Back when I played, everybody had, like a Sherwood stick. It was a hunk of tree. Okay? It was made out of wood. Everybody's stick was made out of wood because I'm old. Okay? Now, a wooden stick is heavy. A wooden stick is stiff. It means it doesn't flex. So if you hit a one-timer, okay, with a wooden stick, you would probably have an arc about this big. The stick would flex a little bit. Okay, I don't know if anyone has seen like what a modern slap shot looks like, but the stick bends to almost 90 degrees sometimes. It's also why modern sticks explode more often. Okay, but it bends a lot. Okay, a wooden stick doesn't bend very much. Okay, but a modern composite stick can flex a lot more. Okay, here's the distance over which I can exert my force. Okay, with a wooden stick, here's the distance over which I can exert my force with a composite stick. And that's on any shot, not just a slap shot. It can be on a snap wrister, okay, any of those things. You get that extra flex, you've got a greater distance over which you exert the force on the puck, which means you shoot the puck faster. Okay, and if you ever watch old hockey games, okay, it is so much slower than it is now. Okay, it's not just because people are faster. The equipment is just that much better. Okay, and everything moves faster as a result. Okay, simple sports science there. Okay, all we did was alter the material of the stick so that we could do more work and give the puck more kinetic energy, have a faster shot. Okay, everybody all right with that? We want the opposite to be true if we're trying to produce safety equipment. Okay, for example, a helmet. Okay? I don't want my head to gain kinetic energy really quickly, or I might get a what? I might get a concussion. Okay, so I wear a helmet. The helmet's got padding, right? So when something hits that padding, it distributes the energy over more surface area of my head. Okay, and that means my head moves less. Okay, my brain inside moves less and gets jostled less, and I'm less likely to get a concussion as a result. Okay, that makes sense? All right, so all of that comes down to work energy theorem, to a very, very simple formula, okay, that is on your formula sheet, and that is this. Work is a change in energy, okay, and that equals force times distance. Okay. Okay, so as an athlete, okay, there's two ways for you to be able to do more work. You work out and get stronger, or you improve your technique, or you add, with that technique, you change your equipment. Okay, equipment can affect your technique. All right, everybody okay with that idea? All right, now there's only one sport that has not embraced this. All of this sports science. Does anyone know what sport has not embraced sports science in any way? Well, let's say the mechanical energy part of sports science. Baseball. Okay? Major League Baseball is still somebody throwing a chunk of horse, okay, at a dude holding a chunk of tree. Okay? I mean, baseball has not changed in that way. Okay? A ball is still a piece of horse, okay, being thrown at a dude holding a piece of tree, okay, and he's going to swing that piece of tree as hard as he can. All right? There is no advances in that part. Okay? Yes, there's some dudes who have worked on the force part by using other less legitimate sports sciences. Okay? Like, yeah, all the roid monkeys who have cheated. Right? Or who corked their bat. Okay? Anybody hear about Barry Bonds years ago? Okay? So Barry Bonds he was a home run hitter. That was all he did. Okay? And he was hitting home runs all the time. And then in one game, he stepped up to the plate and he cracked one. But the bat exploded. Okay? Which doesn't usually, the bat can snap sometimes, but it doesn't usually explode. Okay? The bat literally splintered. And the umpire went out and picked up the pieces and noticed that he had drilled out the bat. So he had put it in a drill press and drilled out the center of the bat and then taken like one piece of the top and glued it back on. So the bat was essentially like filled with cork. Okay? And then the cap was put back on and no one ever really noticed it. Well, what advantage does that give him if he's got a bat that's now essentially hollow? Can you swing a lighter bat a lot faster? Does that mean you hit home runs a lot more? Until some guy throws 100 and some mile an hour fastball and destroys your bat. Okay, so he got caught, took all his home run records away, okay, all of that kind of stuff, because who knew how long he'd been swinging a cork bat? Okay, they ended up finding he had a whole bunch of cork bats. Okay, but that was sports science. Okay, used to cheat. Okay, swinging a lighter bat means I can swing it faster. Okay, here's the advantage of that. We'll talk about this in a little bit. Okay, but the amount of kinetic energy something has is related to how much work it can do, right? So the faster you swing a bat, the farther you're going to hit a baseball. Okay, well that's related to the mass of the bat and the speed you can swing it at, but the speed is squared. So what's more important, the mass of the bat or the speed you can swing it at? The speed you can swing it at. Okay, so he sacrificed the mass of the bat for the speed he could generate because it meant he'd hit it further. Okay, it was a good application of sports science, it was just illegal. Okay, so work is related to two things, the force you exert and the distance over which you exert it. Okay, so the greater the force, the more work is done, because the formula looks like this, right? Work is force times distance. So if I double the amount of force, I push something twice as hard, then I'll do how much more work? Double. If I double the force, I'll double the work. Okay? So if you push twice as hard, you're going to do twice as much work, provided it's over the same distance, obviously. Okay? Okay? Now, mass also affects the amount, not so much the amount of work done, but the amount of energy something will have because mass is part of those formulas. Okay? But force, the more force you exert, the more work you're going to do. Okay? So, an example that we're going to talk about all the time in this course, the bow and arrow, or the slingshot. I mean, they're essentially the same thing. Okay? When you draw back a bow, you pull the ends closer together. Okay? Does that take work? Why? Why does it take work to draw the bow? Because you what?
Because you're pulling really against
You're pulling, yeah, you're pulling them towards each other, and the bow is elastic. What does the bow want to do? It wants to go back to straight. Okay? So if I pull the string back, okay, I'm pulling the ends together, the bow doesn't like that. It wants to snap back to its original position. So when I draw back a bow, I'm doing work because I'm putting elastic potential energy into the bow. Okay? If I release the string, okay, then the bow will snap back, and when it's doing that, it pulls the string with an arrow notched in it faster. Okay? It will pull it through, and it will do work on the arrow. Okay? And then the arrow will shoot out of the bow. So, let's say in that situation that I pull back the bow, let's say I use 100 newtons. Those are the units for force. Okay? To draw the bow back half a meter. Okay, have I done work? Okay, how much? 50 joules, yeah. 100 times 0.5, right? Force times distance. So I will have done 50 joules worth of work. Okay, how much energy is in the bow? What did I do the work on? I pulled back on the string. Did I do work on the bow? How much energy is in the bow? I did 50 joules worth of work. How much energy is in the bow? 50 joules. Work is a transfer of energy. I did work. I transferred that energy to the bow. If I release the bow, how much energy will the arrow have when it leaves? 50. Okay, it has to. It's a system. I do work, okay, I put energy in the bow, I let go of the bow does work on the arrow, okay, energy can't be created or destroyed, out it goes. Okay. Now, this little bit here has to do with how forces work and how they relate to changes in velocity, right? So how they relate to acceleration. So let's say I've got this guy here, okay? In the first situation, he's going to swing as hard as he can at the golf ball. Okay? So in that situation, he's using his maximum amount of force on a very, very small mass. That will produce a very, very large what? What does A stand for? Acceleration, right? The ball will change velocity hugely, okay, by being hit by a golf club. Now, in this situation, dude winds up, swings as hard as he can, and hits that truck. Okay? The truck's mass is enormous. So he would produce a very, very, very small acceleration. Now, how many people are looking at that second situation going, what acceleration? That truck ain't going anywhere. Okay? In the real world, yeah, absolutely. That truck isn't going to roll forward or slide forward because the guy winds up and hits it with a golf club. Okay? But that doesn't mean that it doesn't accelerate. And that doesn't mean that he doesn't do work. He does work in both situations. When he hits this truck, if I'm standing at the front of the truck with my hand on the hood, even if I'm wearing noise-canceling headphones, will I know when he hits the truck? How? The vibration will pass through the truck. Does that mean every particle in the truck has moved? It does. They just didn't move in unison. They vibrated. That counts. Okay? Here's the other thing that will be evidence of work. Wherever he hits that truck, there will be a dent. Okay? That part of the truck moved. Okay? He certainly dented in that part of the truck. That still counts. A change in shape counts. Okay? You at least moved some of that mass. Now, if this was in the perfect physical world and this truck was sitting on perfectly level, frictionless ice, and he hits it, would it slide forward? It would. It would absolutely slide, okay, in that situation. Or if he was out in space, okay, and he could hit it as hard as he could, that'd be difficult because swinging a golf club in space would cause you to roll, but okay, he would be able to move the truck. All right, so force, okay, relates to how much you can accelerate an object based on how big that object is. All right? If I push on that cart, I can accelerate it pretty easily. But if I exert that same force on a freight train, I'm not going to produce very much motion. Okay? Because I'm not Spider-Man, okay, or Superman, or anybody else who can move a train. Okay? The mass is just too big. Okay, so this is what we just talked about with the truck. Motion doesn't just mean movement of an object from point A to point B. It can, okay, it can mean that, but it can also mean a change in shape. Okay, if I change the shape of something, I'm still doing work. And that is evidenced best by elastic objects, like the bow and arrow. Okay, when I exerted the force on the bow, I pulled the ends together. Okay, I changed the shape of the bow, I did work on the bow. Okay, with a spring, the same is true. Okay, if I have this resting spring here, I'm not doing anything to it. Does it have any energy? No, it can't do any work in that situation. What if I, like in this first situation, put my hands on the two ends and squeeze them together? Okay, does that require force? Did I make the spring shorter? Would that be a measurable distance? Okay, I changed the shape, there was a distance there, okay, it counts. And now, for sure, that spring has got energy in it, because it wants to go back. Okay, if I let it go, it'll spring back to its original shape. And the same is true if I grab the two ends and pull them apart. Okay, that's still going to require a force from me, okay, and there's going to be a measurable distance or change in the shape or length of the spring, okay, because it will again have elastic potential energy in it from the work that I did. All right? Everybody following those relationships there? Okay. So yeah, kind of this bit here, okay? Changes in the shape of an object, especially an elastic one, okay, constitute an exertion of force and thus result in work and energy transfers. Okay. This is exactly how like an exercise machine like a Bowflex works. Okay, has anyone ever used a Bowflex before or seen a Bowflex? Okay, so they've got these rods on them and you attach cables to the rods, and when you move the apparatus, you bend these rods. Okay, the rods are elastic, okay, they're basically like a big tough spring, okay, and they want to go back to their original shape, so you have to exert a force on them to bend them and change their shape. Okay, would you get tired after a workout? Because you did all that work, hence the name workout. Okay, the work is going out of you, okay, when you work out. Okay, so we'll talk about this one, then I'll give you a little bit of a break here. Okay, so remember, first day of this unit, we talked about work and heat, both being transfers of energy. Okay, remember that heat, okay, is a change in thermal energy. Okay, work is a change in mechanical. Okay, those are kind of the big things to remember. That could easily be a multiple choice kind of question on a unit exam. Okay, knowing the difference between heat and work. Now, the thing to remember about thermal energy is it is really still a form of mechanical energy, because thermal energy relates to how fast particles are moving. Okay? We measure that as temperature, right? But they're running into each other, and that heat, that thermal energy is transferred by particles running into each other and transferring their kinetic energy to each other. Okay? So when you take it right down to like the particle level, thermal energy still results from a form of mechanical energy. It's still particles moving fast and running into each other. Okay? But on a macro scale, a large scale, it looks a lot different because we obviously don't see the particles doing their thing. Okay, I'm going to give you guys a 4-minute break within the classroom here, okay, and then we'll pick up again. Okay, so we said that work is a change in mechanical energy. Okay, mechanical energy we learned on the first day of this unit. I know it was a long time ago. Okay, but mechanical energy is the sum of an object's potential and kinetic energy. So it's like its total energy. Okay? In Science 10, you're only ever going to be asked to do work energy theorem calculations where either the potential energy of the object is changed or the kinetic, but never both at the same time. Okay? That's physics 20, both at the same time. So your challenge will be to identify in the situation what kind of energy is being changed. So if it's about somebody, like let's say an elevator is taking a bunch of people from the ground floor to the top of a skyscraper, okay? What kind of energy is it changing for those people? Kinetic or potential, assuming it moves at a constant velocity? Potential. They'll be way higher off the ground at the top of the building than they are at the bottom. They're not going any faster, okay? They're not, like, their kinetic energy isn't being changed, but their height is. Anytime the height of an object changes, its potential energy changes, right? If we're talking about kinetic energy, well then the object has to be moving faster. That means work's being done on it. Or moving slower, it's doing work on something else, okay? That's actually how the brakes in your car work. Okay? When you apply the brakes in your car, okay, so you squeeze, when you hit the brake pedal, the caliper with the shoe on it squeezes against the disc. Okay? That creates a lot of friction and turns your mechanical energy, your kinetic energy, into heat. And if you have squeaky brakes, sound. Okay? But it just turns that kinetic energy into something else. You're doing work on your brakes, which is why periodically you have to replace them. Eventually you wear them out. All right, so we're going to talk about gravitational potential energy first. Okay? Potential energy is due to either position or condition. Now, that addresses the different kinds of potential energy. Okay? Gravitational potential energy is due to your position. You could fall. You're in a position where you could fall. Okay? Then you have gravitational potential energy. Condition is related to things like chemical and elastic potential energies. Okay? If you have chemical potential energy, it's because your condition is you're flammable or explosive or something like that. Okay? We don't talk about that in physics. That's chemistry. Okay? The other kind is elastic. So if you are, let's say, a spring and someone has stretched you out, your condition says that you now have elastic potential energy because you've been stretched out or compressed. Okay? So condition means you change something about it and now it's holding energy. Okay? We don't deal with elastic, like in particular formula doing any calculating. Okay? We just deal with gravitational potential energy. All right, so with gravitational potential energy, okay? So gravitational potential energy is the amount of work an object could do because of where it is and some of its other properties. So do we kind of have like a natural fear of things being above us? Right? Like, you ever notice if there's like something that's like hanging off of a crane, people kind of look at it and then they kind of look at where it is and they don't walk right underneath it. Okay? They like walk around. We have this natural fear of things falling on us. Okay? If we look at a slope and there's like rocks that are perched up kind of precariously, we're like keeping an eye on them. Okay? What are some things that could lead us to be more attuned to that object? Like, what are two things, let's say, that could affect how afraid we are of it? Like, am I afraid of a grand piano if it's, you know, just been picked up and it's only this far off the ground? No, because I'm not under it. I don't have to worry about it falling on me. Okay? It doesn't have very much gravitational potential energy because it's only this far off the ground. Now, if somebody has lifted it and they're holding it 10 meters above my head, am I a little more worried about it? Yeah. It's got a lot more potential to hurt me there because it's much higher. All right? Now, let's go to the other situation. I have a grand piano being held 10 meters above my head, and I have a tennis ball 10 meters above my head. Okay? Which one am I a lot less afraid of? Why? Good, the piano will crush me because of its, okay, not weight, starts with M. Mass, right. Okay, weight and mass are not the same thing. Okay? You can really mess with people with that. Okay, weight and mass are not the same thing. We treat them like they are, but that's something we get wrong in physics. Okay, well, not in physics, but in society. Okay, I actually tell people my weight when they ask me how much I weigh, because I like to mess with people, and it's really rude for them to ask me that. Okay, if they say, how much do you weigh? I tell them I weigh 789 newtons. And then at that point, they usually chuckle awkwardly and walk away and talk to someone else, which is just fine with me because I'm an introvert anyway. Okay? But the best part of it is I didn't lie to them. That's exactly what I weigh. My weight is how much gravity pulls down on my mass. It's a force. Okay? I sure as heck ain't telling them my mass. That's none of their business. Okay? But that's what we usually tell people. When they ask us how much we weigh, we tell them our mass in pounds or kilograms. Okay? That's not what we weigh. I could go to the moon and weigh 1/6 of what I weigh here. Then I'd tell people what I weigh too. I'd tell them I weigh like 129 newtons or something like that. Okay? I'd weigh a lot less. Okay? But there'd be just as much of me. My mass isn't any different on the moon than it is here. All right, so the mass of an object affects its gravitational potential energy, and so does its height. Okay, now, I just gave you an example of me standing on Earth and me standing on the moon and said my weight would be different. What's different on the moon versus here? Gravity. There's the three things that affect your gravitational potential energy. The mass of the object, the acceleration due to gravity, little g, and the height of the object. Okay? Intuitively, we kind of understand two of those things. Okay? We're naturally more fearful of heavy objects, okay? And we're naturally more fearful of things that are perched quite high above us. Okay? That's just evolved instinct. Okay? Gravity, well, we only experience one form of gravity in our life, so we don't really get much experience with different gravities. Okay. So if I fall, let's say, hopefully this doesn't happen, but let's say I fall off the roof, just this roof, not far, okay? Could I get hurt? Especially me, because I'm old, okay? But let's say that I fall from that same height on the moon. Will I get hurt? Well, as long as I don't break the face mask or puncture my suit on anything, no, I won't get hurt, okay? Because if I fall off of that, and let's just say it's like, 3 meters, if I fall off from that high on the moon, it's only like falling half a meter. I can fall half a meter, probably not get hurt too badly. You'll understand when you're old and frail. Okay? But yeah, I probably wouldn't get hurt as bad. So G does affect it. The acceleration due to gravity does affect how much potential energy you have because it affects how fast you would get going when you fall. All right, so that's the potential energy formula. Okay, obviously potential energy, that's in joules. Okay, mass is always going to be in kilograms. This number, unless we're told otherwise, is 9.81 meters per second squared because our questions are going to occur on Earth. Okay, and this will be our height in meters. Will that be a fairly easy formula to use? Right? Everything's being multiplied together, so if I need to isolate something, what do I do with the other two things? Just divide them over to the other side. Yeah, super easy to do algebra with that formula. All right. So, gravitational potential energy is the potential energy of an object due to its position. Put your phone in the pocket. Okay? All forms of energy must be described with respect to a chosen reference point or condition. So, reference point for potential energy is usually the ground, height of 0. Okay? For a spring, it would be its unstrained length. So, how long is the spring when nobody's bothering it? Okay? Versus how long is it after I stretched or compressed it? Okay? So, there's always going to be a position or a condition that acts as a reference when we're talking about potential energy. Okay. Let me ask you this as a work energy theorem question. Okay? Work is a change in energy. Okay? Both of the people in this diagram here on the left are going to change the potential energy of the block that they're moving. Okay? Now, we're going to assume, okay, that there's no other forces, no friction or anything like that, okay? They both move their block, the blocks are identical, okay, to the top of that triangle, okay? But one person lifts it there directly. The other person pushes it up the ramp. Who does more work? Who does more work to move their block to the top of the ramp? The guy who lifts it there directly or the one who pushes it up the ramp? Does this feel like a trick? You got to work on your trick sense. And have your trick sense, trick sense tingling here. It's the same. This is the whole purpose of a ramp, right? A ramp doesn't make less work. It makes the work easier, okay? In the end, when both of these blocks get to the top of the ramp, they will be at the same height. They're both on Earth, where G is the same, and they both have the same mass. When they get to the top of that ramp, they will have changed their energy by the same amount. Didn't matter how they got there, they do the same amount of work. But the purpose of a ramp is to make the work easier. You make work easier by exerting less force over a greater distance. Okay? This person here doesn't have to lift the block nearly as far as this person has to push it. Okay, like if we just take this line that I just drew here, right? Like that's way longer, almost twice as long, okay, as the distance over which the person had to lift that. Okay, that's the whole purpose of the ramp. Okay, the inclined plane is the simplest machine. It makes work easier. It is not possible to make less work. This is how the Egyptians built the pyramids. Okay? They did not have help from aliens. Okay? They just had sand and lots of people willing to move the blocks up the ramp. Believe it or not, they've done recent research that says it wasn't all slave labor. Okay? There were lots of people who felt it was an honor to build the pyramids for the pharaoh. Okay? Which basically meant hauling those gigantic blocks up a really long sand ramp. Okay? So what they did is they made the base of the pyramid first, move all those blocks in, and then as the pyramid got taller, they just kept going around the outside of the pyramid and then took all the sand away. Okay. Just made a ramp. Make a ramp long enough, okay, you can move pretty much anything because the angle will be very low. Okay? The steeper the ramp is, obviously the more force you have to exert because the shorter it is. Okay. Everybody all right with that idea? All right, in this situation here, okay, this is what we call a system. A system has more than one mass, but they're connected. Okay? So if I pull on this block, I pull it back, obviously that raises the ball. Okay, so when I pull back on that block, do I do work? Yes. Okay, because I'm going to give that system what kind of energy? Okay, remember when I pulled back the block is sitting on a table, right? Its height's not changing, I'm not changing its speed, I'm just pulling it at a constant speed. But that ball is being lifted. What kind of energy did I put into the system from my work? Potential, okay? I didn't actually put energy in the thing I was exerting force on. I put it in the whole system, because if I let that block go, the ball will fall. And when it falls, it'll pull on the block. Agreed? Okay, so when I let the block go, both masses have to move. Okay, the ball is going to fall because gravity is going to pull on it, but it's got to pull that block along the table. Okay, so will it fall at 9.81 meters per second squared? Okay, think about this. In which situation can you run faster? Okay, if you're just running as fast as you can, or if I tie like a rope to you and attach a rock to it and make you run. And which situation can you run faster? The first one, okay? If I just have that ball and I drop it, it accelerates at 9.81. But if it's attached to something else, it's got to transfer some of the energy to the block, because it has to move the block as well. The block is going to accelerate. Its kinetic energy is going to change. Okay, so there's going to be work done within the system. Okay. Now, could we calculate how much energy that system, or how much work I did in pulling back that block, if I know the ball is 5 kilograms and it was lifted 2 meters? Could I do this? Okay. Delta means change, right? It means final minus initial. So could I do this? Could I say the final potential energy minus the initial potential energy? Since the ball was originally at a height of 0, so sitting on the ground, how much potential energy did it have initially? None. So the only reason that ball has potential energy is because I did work. M times G times H final, so that's 5 times 9.81 times 2, okay? So that should be 98.1 joules. Right, 5 times 2 is 10, times 9.81 is 98.1. Everyone follow my cheat? Okay. All right, so when I pulled back on that block, I did 98.1 joules worth of work, because that's how much energy the system had. Okay. Was that a terribly difficult mathematical calculation? Okay. The method's a little bit tricky, right? Like kind of getting to the point where I can plug the numbers in requires some thought. And that's what basically all work energy theorem comes down to. You're not going to be mathematically challenged here. The trick in these questions is, how do I get to the math? Okay, the math will usually be as simple as this. Okay, but you have to figure out what kind of energy does it have? Where is it? What mass do I use? Okay, what kind of energy? All that kind of stuff. You have to ask yourself a bunch of questions on your way to the solution. Okay, that's the tricky part of physics, not the math. Trust me, if the difficulty of physics was the math, I would not be teaching it. Okay, because I'm not all that good at math. Okay. All right, so we kind of wrote this down earlier, but if you didn't, okay, it's here. Okay, the formula for gravitational potential energy is m times g times h, so mass times acceleration due to gravity times the height. Okay, that gives us potential energy. Now, the units for energy are joules. Yeah. But joules are just the name that we give the units that they actually represent, okay? So we have to kind of look at where the units for joules comes from. Okay, so if I'm looking at this formula here, I'm multiplying kilograms times meters per second squared times meters. Okay, so if I kind of put that all in a line, right, I'd have kilograms over 1 times meters over seconds squared times meters over 1. Okay, that's essentially what we're saying. Agreed? So what's meters times meters? Meters squared. Yeah. Okay, so what's kilograms times meters squared? Kilogram meters squared. And then on the bottom I got 1 times seconds squared times 1. Those are the units for a joule. You can always just write big J, okay, when you're doing a calculation, but it is important to know what the units of a joule are fundamentally. That could easily be a multiple choice question. Plus, when you're doing the math, if you're solving for something other than energy, you obviously want to know what your units are going to be. Okay, so the units for a joule are a kilogram meters squared per second squared. Now, is that making some sense? All right, so let's do this example here, and then we'll kind of, we'll maybe look at one more, and then we'll call it a day. All right, so in this example here, we have a 3 kilogram box lifted by an upward force 1.5 meters above the ground. Okay? What is the potential energy of the box in its new position? Okay, so what do they tell us? They tell us mass, okay, is 3.00 kilograms, and they tell us its height, okay, its initial height is 0, okay, and its final height is 1.50 meters, right? What's the thing they don't tell us that we can just assume? Gravity, okay? Unless they tell you this is on some other planet, we're going to assume that G is 9.81 meters per second squared. All right, and then we just plug those numbers in. EP equals M times G times H, 3 times 9.81 times 1.5. That will require 44.1 joules worth of work because the object will now have 44.1 joules of potential energy. Shanae, tell your friend to go away. Otherwise, I'm going to appear at the window and that'll be really awkward. All right. Everybody follow on that one? Pretty easy, right? Like we're just putting the numbers in and multiplying them together. All right, so let's have you guys try this one. Okay, write down your givens. Okay, write down your formula, manipulate, solve. All right, so you got a 55 kilogram diver on a diving platform, okay, and when they are there, they have 5.40 times 10 to the 3, that's supposed to be an exponent, 10 to the 3 joules. That is 5,400 joules worth of energy. I want you to solve for the height of the diving platform. Give you a couple minutes. So, if we're looking at this one here, okay, our givens are that we know the potential energy. Okay, we're told it has 5,400 joules of potential energy. Okay, guys, listen please. Okay, no packing up yet. And then we've got also the mass. Okay, 55 kilograms, and of course, as far as we know, the only place diving platforms exist would be Earth, where this would be true. Okay, 9.81. So, I need to solve for H. How do I get H by itself? Divide both sides by M times G. Okay, simple as that. So So all I have to do is plug in my numbers here. That'll be 5,400 joules, okay, divided by 55 kilograms times 9.81 meters per second squared. And I forgot to fire up my calculator, so we'll just look at the solution here. Okay, so it ends up being 10 meters. Okay, so this is the high platform, okay, that they use for diving competitions. Okay. All right, questions there? Okay. Just looking at Google Classroom here, I think a few people forgot their lab reports were due this morning. So if you forgot to turn it in now. You can take your phone out and do that if you just forgot to turn it in. Okay, if you didn't forget and it's just not done, get it done. Okay, now a couple other things, okay? Listening here, guys. Okay, reminders, okay, your final exam is June 23rd at 9 a.m. More than likely that will be in the gym, but I'll let you know when they determine the location. Okay, and as soon as I know the supervision schedule, I will set up a Google form for times to sign up for your mock final. I'll probably have maybe like 2, maybe 3 times where you can come in and write it, and also where that location will be, because it probably won't be in here. They usually take my desks. Okay, but we will make sure that that opportunity is there, again, provided you are not missing any assignments. Okay, if you have any missing assignments, then obviously you won't be eligible to sign up. Okay, and there will be a final date for that. Okay, I will put a date up on the board very soon. That is the absolute last day for you to hand in missing assignments. And after that date, I will not accept them anymore. All right. Okay, tomorrow, okay, we're going to continue on with this, but we'll be looking at the kinetic energy part of it tomorrow. All right. Okay. That's it for today, guys. Okay.